Okay. Good morning, everyone. Welcome to our bi-weekly webinar series, where we are talking about the future of civil engineering, how we can improve the technology, what research is going on, and how this research is going to affect the overall future of the civil engineering. So, SIU took this initiative, and we, like a department of School of Civil Engineering, is doing really good job inviting a good young researchers, assistant professors who is doing this research, the advanced level of research, and we are inviting them to have on our webinar series so that we can get the benefit of their research, and the next generation of the students can continue those kind of a work with them. So today I'm really happy to welcome our speaker, Dr. Nikhil Kumar. And if to introduce Dr. Kumar, he is a postdoctoral scholar at the University of California, Davis. He is specialized in hydroclimate extremes, hydrological modeling, climate risk. His research aimed to advance the understanding of water resources and climate resilience through interdisciplinary approach, integrating hydrology, climate science, and social science. So he's working on almost everything and working on the hot topics, which is really needed to work. He is currently focusing on assessing the risk of a compound extreme events, like developing resiliency strategies, particularly in a California region. Uh, Coming to Dr. Kumar, he did his PhD from Indian Institute of Technology, Indore, India. During his PhD, he also received a Young Scientist Award from Madhya Pradesh government, like Madhya Pradesh Science and Technology Department in 2021. During his PhD, he also got overseas visiting doctoral fellowship from Government of India to continue his doctoral research for 2 years, if I'm correct, at University of Alberta, Edmonton, Canada. So he is having a very good background coming, like he worked in the extreme climate situation of the Canada. He worked in the extreme climate situations of India, like he was dealing the similar kind of a research back in India. And then in the US as well, he's working on the extreme climate events and socials impacts and everything. So I'm sure the wide range of international exposure is going to help every one of us to learn what Dr. Nikhil did before and how we can continue. We can take something from his research and we can continue our projects, how we can integrate those climate models and everything in our research. So I'm sure we are going to have a good benefit from Dr. Nikhil today. So welcome, Dr. Nikhil, and I'm really, really happy to have you as a friend. I'm so proud to welcoming you. And I'm sure you're going to help so many researchers today and the faculty members as well. So welcome to SIU and looking forward to hearing you. Thank you.
Yeah, thanks for that like wonderful introductions. Yeah, and thank you everyone for joining. So I'm gonna like share my screen. So is my screen visible?
Yes, Nikhil, it's visible. Go ahead.
Okay, yeah, thank you. So so today my topic here is compound precipitation, wind extremes, and the socioeconomic risks. So what are the lessons that we can learn from this case study of San Francisco Bay Area? So this project, this work is part of a bigger project, which is resilient and equitable urban stream corridors. And if you want to learn more about our project, then you can like scan these QR codes, and you can always contact me for further collaboration opportunities. So, so what we are going to explore today is, so first let me take you back to January 2023. So in California was hit by a series of powerful storms like floods, fallen trees, power outages, all happening in a span of just a few days. So what you are looking at here in this picture, it is not just a bad storm. It is an example of what we call a compound precipitation wind extreme. So these type of events are becoming more frequent, more intense, and more costly. And that's what today's story is all about. So in this talk, I will walk you through what compound precipitation wind extremes are, how we detect them, what the historical data tells us, and what future projections look like. And most importantly, who is most at risk here. So especially here in the San Francisco Bay Area. So what exactly is a compound precipitation wind extreme event? So like technically we say that a compound event, this kind of event happens when both precipitation and wind extremes, wind speed exceed the 98th percentile. So if you look at the graphic here, so this is a daily data of precipitation and wind speed for 365 days. So for day one, and these are the 98th percentile, this is for the wind speed and this is for the precipitation. So when the precipitation and wind speed both exceed the 98th percentile, that is registered as a compound event. So that's a technical definition, but let's make this a little bit more real. So picture this, like heavy rain saturates the soil, like so it reduces its stability. So now imagine that strong winds are also blowing. So when the soil is that wet and the tree roots cannot hold an as well, even the moderate of the winds, they can like knock trees over. So that is how we get blocked roads, power outages, and damages that last long after the storm is gone. So now that we have identified what a compound precipitation wind extreme is, you might be curious about how often these events can occur and how do we calculate their frequency. So in our study, we determine this through a term we use in hydrology, that is a return period. So return period is the inverse of the probability of an event. So if you look at this example, so if we have like 365 days and if we have one compound event in these 365 days, that means the return period of the occurrence of the compound event is 1 year. That means that that event occurs once a year, like on an average. So these calculations are done with the statistical data of like long time series of daily precipitation and daily wind speeds. So a little bit about our study area here. So this is our study area, San Francisco Bay Area, and this is California, and this is our San Francisco Bay Area, which has 9 counties in it, and this map shows us the annual precipitation pattern of the Bay Area. So San Francisco Bay Area is like is a unique area for studying these kind of events. So first of all, the climate here is Mediterranean with wet winters and dry summers. However, if you see the annual precipitation pattern, it varies quite a bit. For example, in this northern counties, that is northern Sonoma County, it receives about over 1100 mm of rainfall annually, while the counties like Solano and Contra Costa, this is Alameda, and this is Santa Clara, so these receive less than 500 millimeters of rainfall. So wet season in the Bay Area, it typically goes from October to April, and which is driven by atmospheric rivers. So what are these atmospheric rivers? These are narrow bands of concentrated moisture that brings like intense rainfall and winds, which leads to increased risk of flooding and wind damage across the northern California. So that makes this Bay Area quite like, since it has a very diverse geography, like places ranging from coastal areas, valleys, and hills, and also a very diverse climate and a unique climate. So it has its unique challenges for managing these compound precipitation wind extremes. So this is our the framework, overall framework that we used here. for analyzing these compound precipitation wind extremes for past and the future. So if we focus on this box here, so what we did is we took the data from 1982 to 2022 from this grid-bed data set, which is at the resolution of 4 kilometers. So we took daily precipitation data and daily wind speed data, and we extracted the 98th percentile thresholds, and after that we defined the compound precipitation wind extremes. So first, we carried out this return period analysis, that is our frequency analysis, and the second part, we did this decadal moving average analysis. So let's look at the results for these 98th percentile and the return period analysis first. So what we are looking here at all these maps are these are the maps of 98th percentile thresholds. This is at an annual scale. This is at the wet season, that is from October to April, and this is for the dry season, that is May to September. And these are the legends of the daily precipitation for 98th percentile, and also this is for the wind speed correspondingly. So like we have selected the wet season here since based on the soil moisture and the storm activity. As I discussed, the influence of atmospheric rivers across the region in this period. So as expected, if you see the precipitation, there is higher extremes in the wet season, and also in the northern and the coastal areas. So with respect to other seasons. So wind, and in terms of wind, we can say that in wind, the wet season, like wind extremes are a bit stronger for the wet season, but not like too much, as there is a difference for the precipitation. So so what we are doing here is we are doing like these two rasters for the wet season. These are our 98th percentile thresholds for defining the compound precipitation wind extremes. So what does the historical data tell us? So how often and how strong do compound precipitation wind extremes events strike? So these first two graphs are the 98th percentile thresholds, and this graph it is shows the return period. That means it shows the like frequency of compound precipitation uh, wind extremes. So the shorter the return periods, more the frequency of these extremes. So what we found here from our analysis was that the Bay Area is clearly a hotspot for these kinds of events, with events occurring almost like annually. And however, like there was an exception of the Marine County, so it experienced lower frequencies than the other areas of the Bay Area. And secondly, if we look at the intensity, like in terms of precipitation, we see that these coastal areas and the elevated regions, they experience the more severe impacts. Like the magnitude intensity of the compound precipitation wind extreme is more in the coastal areas and at the coastal ranges. So this is largely driven by the exposure from or to the Pacific storm systems. That this is the Pacific Ocean, so this is the this is exposed to these storms, and also which is further amplified by the orographic effects, such as wind lifting over these coastal ranges, which runs from here around here. So now that we have like identified the like frequency of these compound precipitation extreme, we move to the trend analysis. So what we did here is we created a 10-year moving aggregate of compound precipitation wind extreme frequency along with a 10-year moving average of precipitation and wind speed and temperature. So this helped us uncover some long-term patterns and the trends. So what the method that we used to do that was that if you see this figure, these are the figure of daily precipitation, daily wind speed, maximum temperature, and minimum temperature. So this is when a compound event occurs. So what we did is, once we identified all the compound events, so we used these different thresholds, like thresholds for precipitation, threshold for wind speed, and we pulled together their characteristics to know how intense they were and when they happened. So when they like this table tells us that when they happened and what was the daily precipitation during that event, wind speed, and what was the temperature was like. So like then we looked at how these events changed over time. So using a 10-year moving time series to smooth out the air to air variabilities. So we looked at trends in frequency all and also in intensity, like rainfall, precipitation, and temperature. So to do this, we use the man candle test and sun slope. So what is this man candle test and sun slope? So this is to understand how these events are changing and to conduct the trend analysis, we took a two-step approach. To first, to detect the trends, we use the man candle test, that is a non-parametric test that tells us if there is a statistically significant trend using Z values. So if the Z value is greater than 1.96, then we call it a statistically significant trend, increasing trend at the 95 percentile confidence level. And if the Z value is less than minus 1.96, then we can say that it has a decreasing trend and statistically significant decreasing trend. So in this example, if you see here in this time series, uh, so we implemented the man-Kendall test, and the Z value was of 3.04. That means that there is a significantly increasing trend here. So as also can be seen in this time series, that okay, we can see that there is a obviously a increasing trend in here. So which is detected by our man-Kendall test. So once we have this, the if our trend is statistically significant, then we calculate the trend slope, sun slope. So this is also a non-parametric test, and it estimates how fast things are changing. So using the median slope between all data point pairs. So as you can see that if we see this, if we take these two values, 2010 and 2011, so the slope value will be 20. So the slope value is calculated for all the pairs, and then the median slope value is the sun slope value. So which in this example is 18.57 mm per year. So which shows that it has a positive magnitude of change, as also is reflected in the time series. So these are the two trends that we use for conducting the trend analysis. So in this figure here, what we are looking at is how often these events are happening over time. So this is just based on 10-year moving averages. So this graph, this tells us the mean frequency of the compound precipitation wind extremes, and this tells us the magnitude of change. So on an average, what we see is we see about 14 events per decade across the Bay Area. So that is more than 1 year in many different places. You can see this graph here. So what's even more important is the map on the right side here. For a large portion of the region, it has a statistically significant trend, and the frequency of these events has been increasing in the recent decades. That means that the compound precipitation wind extremes, they are more frequent in the region, and they are becoming more frequent. They have become more frequent in the recent decades. So far, what we have seen is the frequency of the compound precipitation wind extremes. Now, in this slide, what about how we see how intense they are? So So these two graphs, these are for the like mean precipitation and the trend analysis for the precipitation, and these two graphs are for the wind speed mean and the sun slope of the wind speed. So in terms of the precipitation in during these events, what we see is we see a like it shows a significant increase. Many areas see an upward trend of 0 to zero point 0.5 mm per year uh, in this last 40 years. So and in terms of wind speed, in contrast, like with the wind speed during the this compound precipitation wind extremes, it's decreasing, and most of the Bay Area it shows a negative trend. So what we learned from this analysis of the past. So to wrap up here, the San Francisco Bay Area is a global hotspot for compound precipitation wind extremes, and with return periods ranging from zero point 0.5 to 2 years, meaning that these events occur almost annually in most areas. Second, there is a clear increasing trend in these compound precipitation index streams, and which is likely driven by the broader impacts of climate change on these extreme weather globally. And also, uh, these events, the compound precipitation in wind extremes, their trends. They show increasing frequency and intensity of the precipitation. So now, like we know this about the past, and now where do we go from here? So the future work will use climate models and different climate scenarios. So before we dive into the future projections, let's quickly talk about the engine behind them. So those are like global climate models. So what are these global climate models? These are complex numerical models that simulate the Earth's climate system, and they factor in things like atmosphere, oceans, and lands. So these GCMs they use different climate scenarios as the input to simulate possible future climate conditions. So like in this global climate model, what happens is we divide the Earth into 3D grid into like like the Earth is broken down into these cubes, and at every cube these key processes are modeled. So the key processes like radiation, heat, moisture movement in each cell are modeled. So in short, that these models are our best tools like for now to understand what future climate might look like. So these global climate models they input different climate scenarios. So what are these climate scenarios? So we have two types of climate scenarios. So one is representative concentration pathways (RCPs), which were defined in the previous reports, like the defined by IPCC AR5, and the latest ones are these shared socioeconomic pathways, which are have been described in this report IPCC AR6. That is, these are reports given by Intergovernmental Panel for Climate Change, and so these like tells us the about the current risks, and also like what is the expectation of the future risks of the climate change. So so these are the two different scenarios, and how they are related is like RCP 4.5 is an intermediate scenario. That means a middle of the road development with like moderate mitigation efforts. So these two are equivalent, and the RCP 8.5 and SSP 5 8.5, these are high emission scenarios, and like that means that we don't do anything in terms of climate adaptation, and uh, the development is fossil fuel based, high inequality, and there are very limited mitigation efforts. So, so if we see this graph here is on the y-axis, it tells us about the CO2 equivalent. like today's CO2 equivalent is 429, so we are somewhere about here. So these are the different trajectories that our future might look like. So in RCP 8.5, the future might look like where the CO2 concentration will increase up to 1200 1200 ppm uh, towards the end of the century. And these are RCP 4.5, and these are four different scenarios. So in this study, we are focusing on the one moderate scenario, that is SSP 245, and one high emission scenario, that is SSP 585. So so if we look at this box here, so we are as I said that we are using these two future scenarios, SSP 245 and SSP 585, used from this CMIP 6 data set. We are doing the same thing, like we are taking the daily precipitation data, daily wind speed data, um, and based on the 98th percentile, we are defining the compound precipitation wind extremes for the future. So, like, to explore how these extremes change in the future, we are using this downscale dataset, CMIP6 dataset. It has 7 CMIP6 models and 2 SSP scenarios. So, and the daily data it is at the resolution of 4 kilometers. So data is produced by Oak Ridge National Laboratory, and like this is kind of the homepage, what looks like. Uh, So also, so for the future changes in these compound precipitation wind extremes, they are assessed for two periods, uh, 2034, 2034 to 2066, and 2067 to 2099. So in this slide, what you see is these are the rasters that were used to define the compound precipitation wind extreme in the future analysis for all the GCMs. So, so these maps, they are the observed 98th percentile threshold based on observed data. So these are the threshold that we used for conducting the future analysis. Like why we are using these thresholds is because each model can have different thresholds. So to ensure consistency, we apply these observed thresholds to both historical data and future data. So that's way we are comparing apples to apples. So so what this slide shows is here, it shows us the return period of compound precipitation wind extremes from these 7 different models. Each of these maps show historical return period from individual climate models. So these are the 7 models. And so what we are doing here, to summarize across the models, we calculate the ensemble mean. That is, we average the return period at each grid point across the 7 models, and we get this raster, like that is an ensemble mean raster. So for the future projection, we are summarizing the results from all the models using this ensemble mean approach, and which is the same averaging method is also applied to the compound precipitation wind extreme intensity characteristics, like that is precipitation and also the wind speed. So now what the future looks like. So these are the future changes in return periods, like how the frequency is going to change in the future. So this is the, like, simply the percentage change. If the percentage change is increasing, that means the lower frequency, and if it is decreasing, that means the higher frequency. And these plots, they show, like, out of the 7 models, like what is the number of GCMs supporting the change signature of that. So under the SSP 245, both in near future and far future periods, we have negative change across the Bay Area. That means, like, the frequency would increase. And for under SSP 585, that there is a positive change in most of the Bay Area. Uh, so that means there will be less frequent compound precipitation wind extremes. So though there is a like medium model agreement across these projections, so like we have a very diverging future trends in terms of compound precipitation wind extreme like frequency under different scenarios here. But like, what about the precipitation intensity? So what like future precipitation intensity in compound precipitation wind extremes look like? So as we can see, this is the percentage change and this is the level of agreement across the models. And we see that in both the scenarios, there are increasing intensity of compound precipitation wind extreme in terms of precipitation in both near future and the far future. And there is a high model agreement across these projections, which reinforces the confidence in these projections. So this graph, this what it shows is that it is the average daily rainfall during the compound precipitation wind extreme in the Bay Area. So from 1982 to 2099. So this dotted one is the observed time series, and this black one is the modeled time series for the historical period, and the red line shows the SSP 585 scenario, 245 shows the uh, SSP 245 scenario. And the shading represents the model spread, that what is the maximum and minimum in that case. So as you can see that we can, if we compare it with the historical, it is the precipitation during this kind of event is increasing. Both scenarios show that it is increasing in terms of precipitation. So what is happening in terms of like winds, or what does future wind intensity looks like? So there is a very little change or weakening in most areas. So we have minimum projected change in wind speeds, which lies between minus 1.5 to 1.5% only, and with a very moderate model agreement on this stable trend. So, so far, like here's what we have learned from these compound precipitation wind extremes from the observed analysis and the future analysis. From observations, what we found that the San Francisco Bay Area is already a hotspot. It is experiencing near annual events, and these events have become more frequent and more intense, especially in terms of precipitation. Now, looking ahead, the projections show that these compound precipitation events are likely to intensify further. And while like precipitation will increase, wind speeds would remain mostly unchanged. The critical insight from here is that the Bay Area it remains at risk, and the compound precipitation they are like in terms of intensity they are in that it is increasing. So on the right hand side, you see an image that grounds this science in reality. Like it is a reminder that these extremes, they are not just abstract concepts, they directly affect lives. So who is at most risk here in the San Francisco Bay Area? And what happens? So this is a very critical question in our research. Like what happens when climate meets inequality? So it's so globally what we have seen with the climate change, there has been increase in frequency and intensity of extreme weather events, making this a pressing issue for urban regions worldwide. And the San Francisco Bay Area is no exception here. As one of the most critical urban regions globally, it is home to over 7 million people and it has a big economy, like 750 billion economy. But there is also a downside, like um, apart from this $750 billion economy. Like it is also a hotspot for extreme weather, as you can see in these visuals here. And and like for these compound precipitation wind extremes, when they coincide, they are often driven by the atmospheric rivers. So, and there also exist significant like socioeconomic disparities within the San Francisco Bay Area, as we can see in these visuals, uh, and which needs to be addressed. And these extreme weather events which are happening here, like somebody is at most risk. Uh, so who is at most risk? We calculate that in terms of the social vulnerabilities. So now we have understand the patterns of the compound precipitation wind extremes in past and the future, let's explore how these events intersect with social vulnerabilities in the Bay Area. So next we focus on the socioeconomic analysis, which integrates like social vulnerability and the hazard, the exposure with that we get from these compound precipitation wind extremes. So what we have done here is that we calculate the hotspots where the high frequency of compound precipitation wind extremes matches the high social vulnerability. So like how are we calculating this social vulnerability index? So this social vulnerability index, it is a tool which is used to like assess a community's ability to prepare for, respond to, and recover from the disasters. And so this is based on the American Community Survey 5-year data sets. And this SVI rank, like it has 16 different variables, and which has four key themes: the socioeconomic status, which includes variables like poverty, employment, and housing cost burdens. And the second theme is household characteristics such as age distribution, disability status, and single parent households. The third theme examines racial and ethnic minority status. And the final theme addresses housing type and transportation challenges. So so each variable, like each of these variable, it is ranked using a percentile method which compares a census tract data relative to others. So these rankings are combined to produce this overall score of SVI. So wherever the SVI is higher, there is higher social vulnerability. So this like SVI, it identifies that which communities they may need additional support during the disasters, which can guide resource allocation and further interventions. So So these are the results from for the four key themes. This is for the socioeconomic status, this is for the household characteristics, this is for the racial and ethnic minority, and this is for the housing type and transportation. So what we found was that the finding of social vulnerability index here was that so there is the within within each county within each county there was a significant intra-county variation. That means like we require localized like policy intervention to address these specific vulnerabilities. We cannot take decisions at a county scale. We or so because there are some hotspots inside very rich counties as well, which needs to be addressed. So So, or also what we found was that these urban areas such as Oakland, Richmond, San Jose, and Hayward, they demonstrated consistently high vulnerabilities across the different themes. And in rural areas, the counties like Napa, which is here, and Sonoma, which is this one, they show elevated vulnerabilities due to factors like mobile homes, lack of transportation access, and group quarters. So in general, what we found was that if you look at this racial and ethnic minority, so this racial and ethnic minority in Marine County uh, and Sonoma County, there it's very less. And what we found was that wherever this racial and ethnic minority, it is mostly driving the social vulnerability. That means the like people of color with socioeconomic status that it has a uh, uh, this trend is a well documented trend across the United States that people of color like always are associated with lower social economic status. So these results, like again, emphasize that the need for a localized policy intervention tailored to address the specific vulnerabilities for both rural, urban communities and also for across the race and ethnic communities. So here, this slide, what it tells us, the intersection of both our results from the social vulnerability index that we got from this analysis, and our like return period analysis, that is our frequency of compound precipitation extremes. So we have established that this Bay Area is a compound, it is a frequent hotspot for these kind of events. And so what is the intersection with the social vulnerability here? So what we found was that is the Marine County, it stands out for its resilience with very few compound precipitation wind extremes and also lower social vulnerability compared to other areas. And however, the key urban centers, that is like around here, Richmond, Oakland, and Vallejo, San Jose, and Santa Clara, they face both frequent compound precipitation wind extremes and heightened social vulnerabilities. So, let's pause and take a stock of what we have learned so far. So, the San Francisco is already a hotspot for compound precipitation wind extremes. Both observed data and future projections, they point to rising intensity of, especially in terms of precipitation. However, the winds, they stay mostly stable. But what truly raises the concern is not just the compound precipitation extremes where they are occurring, but it's also who is at most risk. So, in cities like San Jose, Richmond, and Oakland, which see a dangerous overlap between high compound precipitation wind extreme frequency and elevated social vulnerability. So this makes one thing clear, that we need to reduce the future risk. We need targeted, like transdisciplinary collaboration that integrates climate science, social science, and urban planning to protect those most at risk. So these are my references, and yeah, thank you for listening. Thank you, everyone.
Hey, thanks, Dr. Nikhil. Nice presentation indeed. Like you shared a lot of things. I think they'll take time to process it for sure. So let's open for a Q&A. I think somebody is typing. So let's wait for a couple of minutes. If you want, you can stop sharing.
Sure.
Okay. Any question, participant, please go ahead and ask. If you want to unmute yourself, feel free to unmute. Any question? Okay, meanwhile, they are thinking about the questions and oh, okay, we already have questions. So can you take it from the chat directly?
Yeah. So yeah, I think Arash has asked a very insightful question here. So, the question is that can you compare the combined effects of wind and precipitation when they occur simultaneously, we have done in this study, versus when precipitation is followed by strong winds? So yeah, so in this study, what we looked at is we looked at only like specific days. We are not looking at like if precipitation happened, and we are not having any lag time for that, uh, for for the impact. But surely it is a very good like insight. And so in the future, also work, what we are considering is we are considering like this work was done for a daily data set, but we are also considering doing it for like 3 day data set or 5 day data set. Like what does 3 day precipitation event 3-day precipitation and 3-day wind speed, and compounding of those magnitudes looks like in the future and in the observed period. So yeah, that's also going on and in process right now.
Okay, good question, Arash. Arash is going to be my first PhD student joining SIU. Uh, okay.
Great.
Any other question from the participants? No question? Okay, so Nikhil, what advice do you have for the researchers who is working on the hydrological climate models and everything? Today, actually, today we have a water workshop here going on. So most of our water people are engaged in this workshop because the 120, 140 students are visiting the school students. They're getting some training on water. So they are literally, so like most of our students and faculty members who is working in the hydrology area, they are busy there. But what advice do you have? Like, what kind of a research they can continue and what scope they can explore more? Like, what is an untouched area? And do you have any advice for the young researchers who is working in this area?
So like in terms of like some novel questions to be answered, like there are studies for extreme events, or like, and people are doing studies on extreme events with some advanced methodologies. But where I can see that like how we are integrating the like extreme event analysis with the social sciences and what is their real world impact, there are like fewer projects focused on that. So I think like some kind of integration of all of the disciplines to come up with like very like stringent and very confident a policy approach, so to like that, that can be done in our research. And I think like even funding agencies would love that kind of work, since the if any department can be told very specific directions that what to do at the field scale, so that would be very encouraging. And like for example, like what in the project that I'm working on, it is a multidisciplinary project. The part that I am doing is just a key, and like it is a whole like it has a social science component, other social science component where we are also like interviewing unhoused people in the Bay Area. So what are their challenges? We are like going into the field and interviewing them. There is another component which is a very which has a which is at a stream scale. So we are going to the field and we are surveying data, like how wide is the river at what scale, and how does the like how does the same intensity of flood impacts differently across the different streams. So all of this like is if it comes together and if it boils down to some very like specific guidelines for the departments, like concerning departments, I think that would be really good to do that. Yeah, that kind of research. And like
Okay.
interdisciplinary and applied in some sense.
Okay. So we have question again, the another question from Deepak. He said, considering the increasing frequencies of the compound precipitation and wind extremes due to the climate change, how the urban infrastructure is high risk area like a San Francisco area is designed or adapted to reduce the socioeconomic vulnerabilities, especially marginally communities. So do you have any insight on that?
Yes, I think that's a great question. Like we are like everybody is still struggling with the like in our project we also work with the like organizations which are doing work on the ground with these with these marginalized communities like unhoused people,
Mhm.
and like there is a urban housing crisis in the Bay Area, and that is the Silicon Valley, where multi-billion industries and that's there. So it mostly depends on. So there is a hazard, like it is increasing. But if we see it from a very risk point, then the people who have the coping capacity to to recover from that hazard, they are not vulnerable. Who is vulnerable? Those people who don't have the coping capacity. So like the intervention should be to increase the coping capacity of those particular communities. For example, if there are people if there is a housing crisis and unhoused people, so we have to take care of those people, and we have to uplift them using different like interventions, like whatever they need to uplift them, to increase their quality of life, so that they can have a house, and they can, so they can reduce their vulnerability towards these risks.
Got you. Yep. I hope it answered Deepak's question. Any other question, participant, go ahead and ask. Meanwhile, I'll ask one more question to Nikhil. So, Nikhil, when we collect those data, like for example, the precipitation data and even any other climatic data, so you must have some kind of equipment errors, sensors errors. So what is the reliability of those data? And how do you modify or work like for example, like you install 20 sensors may be giving a 20 different results, and you need to map them on the same scale because you are going to consider them as the same like magnitude or something. So how you tackle this challenge of having the equipment variability in your data set?
Mhm. So I would say, like if we have multiple equipments to measure the same thing, like even if like, so we can take a uncertainty approach. Like we can take a, like, what are the different range of like possibilities, uncertainties that is possible. We incorporate that in our analysis, and then we like move forward with that. Like as I show with the like climate change analysis, in the future we are doing like analysis with the 7 models. So there are, we can take one model and we can do the analysis with one model, but we are
Mhm.
taking 7 models and we are incorporating the data of all the 7 models and the uncertainty, like, because there are different possibilities. Each model has a different possibility, each scenario has a different possibility, so we have to take all the uncertainties into consideration. And like, yeah, it, the analysis is much complex, but I think it is important to also state the what is the confidence in these projections, that we are like saying that it is going to increase, but okay, how many models say that it is going to increase, and how many don't say that increase, and why? So these are also the questions that are to be addressed in our research.
Okay. Yeah. So, falling to the same question, which you already answered a part of it, which I was about to ask. But whenever you design these kind of hydrological models or hydroclimatical models, what is the confidence level of those models? Like, and what is the accepted confidence level in general in the field of hydrological things?
Mhm. Okay, so I would say I will take an example of the hydrological model.
Mm-hmm.
So, like for a hydrological model, like in general, like what we do is we compare the like observed discharge with the with what we are getting from the hydrological model, and
Mm-hmm.
if the Nash set cliff efficiency, and that is a measure to use this to compare these two time series, it is more, if it is more than zero point 0.7 at a daily scale, it is very good, and if it is more than zero point 0.8 at a monthly scale, zero point 0.9, then yeah, we can use that in our analysis. But also like but there are like limitations to that as well. Yeah,
Okay.
it's a with a grain of salt.
Okay. Okay. The last question from me though.
Yeah.
So seeing your results or your analysis, which you did like a compound integration of wind and precipitation together. So how much we are ready as a United States with our infrastructure for these kind of extreme climatic situations? Like, do you have any insights or any suggestion on that?
I think like uh, in terms of infrastructure, like I think United States is quite right. It is ready for handling such kind of extremes, but then also like it like but there are devastation, as we have seen in in the past, that in right now, like in this winter, Florida, it always gets tornadoes and there is mass devastation. So yeah, like there is a need to like increase the coping capacity of people. I think in terms of climate change, it is now the things have become so unexpected that like even the observed data that clearly shows a signal that frequency, intensity of extreme events, it's going to increase, and it is general everywhere. So in terms of that, what we can do is, like as I showed the CO2 equivalent, we can also focus on the mitigation policy, that is from a very global policy perspective. But at a very local scale, it is important to increase the coping capacity of the like communities which are exposed to such disasters.
Okay. Okay. Do you mind to take one course more question from Arsh? It is in chat.
Sure,
A long
sure,
question,
sure.
so I don't want to read. You can go ahead.
Okay.
So meanwhile you're reading, I can read for the participant. So have the effect of a different soil types like a clay, sand, or gravel, gradations, and the mechanical and physical properties of soil has been considered for these models. So he is more into like, soil
Yeah, yeah.
mechanics or foundation. So he is just trying to understand, are you considering those discrete element models? I don't think so it is considered in this kind of hydrological models, but you may answer better.
Yeah, exactly. Because uh, so like obviously we are not considering such a very specific information about the soil, but surely when we do hydrological modeling, like
Mhm.
some distributed hydrological modeling, then we like also incorporate this soil information into our hydrological models. So this the data that I've shown here is it's only climate analysis. So what is and what when that climate meets the ground and results into floods, we haven't shown that part yet.
Right,
So
right.
yeah, but in that part, in terms of hydrological model, we are doing like we are incorporating the soil data and everything. It is a very physical based process mechanism, so that all the different processes, what is happening in the groundwater and and in terms of soil moisture, is simulated well enough in our hydrological model.
Okay.
Yeah,
Yeah, that's great. That's great. Thanks, Nikhil, for such a nice presentation. I'm really impressed, and like, I'm sure today the participant must have got some insightful information related to extreme events and how those extreme events can be handled. So because first step is to understand those extreme events before we go ahead and do any flood analysis or infrastructure assessment or anything. We need to understand what is the impact of those events. So thank you for sharing this timely presentation, a very nice presentation. And I'm going to share your email ID with all the participants. So if they have some questions, they will definitely bother you and
sure,
like
sure,
they'll
sure.
just send you.
Yeah,
And I'm
yeah,
sure you are a nice person. You're going to help them for sure. And for the participant, I'm going to post this like a recording on YouTube very soon, maybe within a week. You can go back and watch Dr. Nikhil's presentation, what he present, and if you have any question, feel free to ask him. Uh, Happy to have you, Nikhil, today, and thank you so much.
yeah. I think thanks for inviting me. It was really lovely to be invited, and yeah, to share my work with everybody. And yeah, for all of the participants, please feel free to reach me for any collaboration, any questions, anytime. Yeah, I'm here. Yeah, thank you.